Hi, everyone. My name is Aisha Jallo. I am one of the facilitators for today from NIH. I'm also going to have Wisdom introduce themselves.
Hi, everyone. So my name is Wisdom Akurugu, and I am based at the Coordinating Center here at UCT.
Great. Let's start with everyone introducing themselves in the chat while I explain some ground rules for today's session. We're going to ask for the participants to ask all the questions at the end once all the presenters are done. We can go ahead and start with the first presenter, Cynthia and Andy.
Hi, folks. Cynthia was unfortunately not able to come, so I'm going to be speaking for the Odyssey Network, and I appreciate the opportunity to be allowed to actually come and talk to you guys today, coming as an outside group. We have talked a little bit to the DSI Africa folks before, but this gives me an opportunity to talk a little bit more about the specific, not just the Odyssey Network, but some of the core tooling or opportunities for collaboration within DSI Network for all the work that you guys are doing. So Odyssey is the Observational Health Data Sciences and Informatics Network. I'm director of the Columbia International eHealth Laboratory at Columbia University. We do the CL terminology, which I'll talk a little bit about in a minute. But I'm sort of here representing in particular the sort of global network of people who are using open source and open science tools to do research. Odyssey's mission is to improve health by empowering a community to collaboratively generate the evidence that promotes better health decisions and better care. So it's not just about research for research purposes, but really how to use observational research to drive improvements in care and ultimately improve healthcare for people. Just to give you guys an idea, Odyssey has grown considerably over its time. It grew out of the original OMOP consortium, if you had heard of that, maybe the OMOP data model. But as you can see now that there's over 3,000 collaborators in 74 different countries. One thing you'll notice here, though, is that there is a relative dearth of people working within Africa, specifically in the Odyssey network. And there's this new working group in Odyssey design called the Africa interest group that is working to improve that and get more and more data sets and data collaborators from the African continent. If we truly want to be representative of global health data, it's important that we have everyone represented. What Odyssey actually is, it's actually a collaboration that allows people to essentially take a federated data set. So in other words, data in your own country, within your own facility, your own institution. It standardizes into a common data model across all of different institutions, and that you can then apply a standardized and open source tooling to actually analyze that data and share the results. So the data never leaves your country. The tooling is available and developed by the Odyssey community, one of which I'll talk about in a minute. And that you are able to participate in these network studies by simply downloading the study protocols and being able to run them against the standardized data model and database that you have. So it's a very powerful environment and network that allows people to participate relatively easily, as well as for them to actually generate their own research questions and then submit them to the global network for other people to participate in. So the idea here is that there is a series of tools that allow you to standardize your information that you are currently carrying in your own country, mostly health-related information, although I will say that there is some spreading into more ancillary or related data sets, but primarily patient-related health information. Those are stored in a common data model, and actually also standardized in terms of the terminology and the coding that's used that allows you to essentially leverage an open source tool, an open source query, regardless of where your data is in the network. This is one of just a quick view of what the OMOP Common Data Model looks like, but you can see that there is, areas for operational pieces of healthcare, as well as conditions and procedures and outcomes, laboratory results, and so on. This model allows different data in different countries and different facilities to be looked at or viewed in the same way. And as you can see, there's 331 current data sources, 284 different EHRs in 34 different countries. And as you can see, there's about over 750 million unique patient records in these OMOP/Odyssey databases around the world. One of the key aspects of getting that data to be normalized is to actually ensure that not only is the structure of the data similar between each of these facilities, but that if you're talking about malaria in one place and malaria in another place, that it's the same malaria. And so one of the very important components of Odyssey actually is a terminology infrastructure that helps map whatever your source system is, including there's a natural language processing component that may use non-structured data, but any structured data to a set of standardized concepts, which are then used by those queries that I just mentioned. So you can see it's a rather large terminology infrastructure. And I'm going to specifically talk a little bit of how we're trying to get Africa to participate by having African related terminology included. And the way we do that is actually through CL, Columbia International eHealth Laboratory, which originally developed their terminology as a way to analyze the Millennium Village Project data, which was in 10 sub-Saharan African countries, but it now is in some 40 different countries. And this data set is essentially LMIC/Africa related. And the kinds of data elements are not just procedures and diseases and laboratories, but also observational questions. How many nights did you sleep under a bed net in the last week, for example? And this data set is all mapped to the standardized codes. So what CL is doing is helping to ensure that the source data is actually converted not only into the OMOP sort of framework what Odyssey does, but it has the right codes attached to it. So the right ICD codes, SNOMED codes, LOINC, RxNorm, and so on. And because this is such a big lift, that's what we perform for anyone. You can subscribe, it's open source. This is the link that you can use to get to it. And you can learn more about how to use the CL dictionary or how to use the Odyssey toolset to help normalize your data and to standardize it. If you go to the odyssey.org website, there's a working group dropdown, and you can see right there it says join our work groups. You can see the African interest group there. We would love to have people participate. And if you have any questions about this sort of the challenge of taking digitized data from point of care and normalizing it into standardized codes, and then using those in some sort of standardized open science network for analytics, I'd be happy to answer questions. So thank you very much for inviting me to talk, and look forward to anything, discussion that comes out from this.
Thank you, Andrew. Next, we have an Emil presenting.
Emil, can we hear you?
Yeah, can you hear me?
Yes, good.
Yes, we can
All
hear
right,
you.
so this is Emil, actually
You're not
Professor.
in presentation mode though. You need to switch back to the
Yes, presentation mode, please.
display settings.
It is already presentation mode. Can you see my slide?
Yes, but we do see some notes also. So maybe
really?
just check it on. Yeah.
Yeah, so if you go to the upper where it says display settings, there's a drop down. I think you can switch the
Yes.
display. In the upper menu bar there, it says display settings.
Let's go down. Yeah.
Yeah, now click on the display settings at the top, and you can switch.
Oh. It is already I've already put in the presentation mode. I can see the presentation
No,
mode from my side.
Yeah, but we're not seeing it. You need
Really?
to switch.
Yeah.
You need to switch the display.
We
It's
need
already.
it's still a little bit.
You're doing the right thing. You just have to switch it after you do that. So maybe you can't see. Are you unable to see the display settings at the top? Maybe you have to do.
Okay,
tab.
sorry.
You may have to stop sharing and start sharing again, and
You
then
have,
you can.
you have two screens, so you have to switch to the screen that.
Yeah, what I'm gonna do.
Or just go the way you were going.
It means you're not sharing the presentation mode screen.
If Faisal suggested F4 or F5, I guess the switch.
Okay.
See my screen now.
Oh, it's
Got
Yes.
it.
yeah.
Great.
Go ahead. You're great.
Hello, can you hear me? Can you see my screen?
Yes. Emil, can you not hear us?
Can you see my screen?
Yes,
Yes, we
Emil, we
can
can
see.
see.
Can't hear.
Continue.
All right, so sorry about this technical issue. So I'm a professor of bioinformatics and computational biology at Northumbria University, Newcastle. So I want actually to talk a little bit part of what we do in my research group, which is actually oriented to disease risk predictions, which is actually a lot of things has been done in this area. So however, the predictive power of current disease risk prediction model vary with genetic ancestry. And we have done some research on that using UK Biobank, where we compare all continental populations. As you can see from comparing all continental global population from European, American, East Asia, South Asian. So there is a kind of variation in a risk prediction power between continental population is even less power in African population, and still variations in predictive power. So we actually benchmark current progeny score tools to actually understand how those tools can actually be able to reproduce the predictive power. And as you can see from this figure, actually all the tools have different predictive power, and none of them reach the full predictive power, which actually indicate that those tools, they don't actually account for certain information such as environmental modifiers, ancestry variations in terms of local ancestry or global ancestry as well. So therefore, there is a kind of loss of information in the current models of disease risk predictions. So that actually reduce their accuracy and portability. And of course, that raises a major question on how those tools can be equitable in a clinical utility perspective across diverse populations. So there is a need actually to investigate multiple causes that reduce current disease risk prediction power and their portability across diverse populations. and to find a way we can leverage data sciences or machine learning to predict power and boost the portability of disease risk prediction in diverse populations. So what we actually hypothesize that is that by leveraging ancestry informations and other population genetic information and also incorporating ancestry specific variations can potentially unlock portability issue in current disease risk predictions. And then for this particular research, we try to build PredictMix, which is a tool that will actually increase the predictive accuracy, the power, and the portability of predicting disease risk across diverse ethnicity. So what we actually we'll try to implement a framework that's actually group a lot of population genetic factors and a novel statistic, a combination of novel statistic models to be able to reach the accuracy and also to be able to apply the risk prediction in a real world scenario, or at least to have clinical utility on that. So, and we believe that PredictMix, with the support of some collaborators from UK and Africa, will achieve this main goal. So here I'm going to try to give you a little bit of how it works. So we'll try, first of all, in the first step, to refine polygenic risk score by accounting for several population genetic elements, such as natural selection, mutations at the individual level or in population level, the variance of local ancestry and the global ancestry at individual level. And then we will use a kind of a Bayesian hierarchical model with lasso regressions by leveraging penalty functions as a prime, which will be kind of full Bayesian models. Once the polygenic risk score has been refined, we'll now integrate polygenic risk score in a full disease model where we account for family history, some demographic informations, and the clinical parameters and the lifestyle of individuals to actually be able to fully predict the disease risk predictions. At that level, we'll try to actually apply a select feature model where we're gonna actually go with relevant predictors according to the individual's ethnics or background or socio-demographic information that is in our hand. Then we will actually apply for individual disease risk prediction, apply a simple logistic regression classified models. And then once the individual disease risk prediction has been inferred, then we're gonna actually stratify the model by doing stratified disease risk predictions, whereby we're gonna actually apply a supervised mixture elliptical copular models. So this has been done, and then the plan to actually try to benchmark this tool is to use a large scale data in public domain like a dbGaP, UK Biobank, where we will focus on cardiovascular, prostate cancers to actually benchmark this tool, and also use some tool for simulation where we're going to actually benchmark this tool PredictMix against existing tool. Then for real scenario, we'll actually partner with a kind of clinicians to actually fund a real world scenario of PredictMix, where we're gonna actually try to go from population level predictions to individual or patient at the clinical level, how we can predict prostate cancer in individual, where we're going to actually leverage the whole genome sequence data of prostate cancer, and we will benchmark that in prostate cancer and also joint replacement. So the overall picture of PredictMix is actually have a back end, actually which has actually built from a cloud, where we actually develop a LAC framework that actually integrate a lot of database from disease symptom, from nutrition disease, and also the patient information that we have here. And those models will actually operate at a mobile phone of the patient to actually display the risk prediction and provide a real-time decision support on the element that the patient have to do or to prevent or to decrease the risk that it got from the score that has been predicted. So on the other side also, from the mobile phone, we're gonna actually in real time actually collect the data from the patient via the phone or via electronic chemical biosensor that I will go to the detail. So there's a framework from the two that operate from the mobile device, whereas the device to collect data and to provide the output from the risk predictions. And also on the back end, where we call actually is the personalized artificial intelligence tool for predictive prediction, disease predictions, which is actually developed with the support of AWS. So here I have to acknowledge people that fund our projects. So we have some UK network, and we also receive some funding from the Academy of Medical Sciences, £1 million. And we got support from also Amazon that's actually support us to build the back end of the data lake side of the project. So this at the end here, this is my email and this is my contact detail. If there's anything that can be interest to you, that we can explore collaboration, so I'm available to take it up. Thanks very much.
Thanks very much, Emil. Can you exit your presentation mode, and then we have the next speaker. And so we have Tesh from.
Yes,
Yes, Tesh, just go ahead.
sharing slides. All right. Can you see my slides?
Yes, but put them in the presentation mode.
Yeah. Let me swap it. All right. Thank you, everyone. My name is Tesfaye Mersha. I'm a professor of human genetics at the University of Cincinnati Children's Hospital Medical Center. So I'm going to talk to you a little bit of the research activity, which entitled Research Education Programs in Health Data Science in Ethiopia. So we collaborate with two universities, University of Gondar, University of Bahar Dar in Ethiopia, and actually some of our works goes beyond the two universities. So first, I would like to outline the organization that we created to support data science in Africa. We call it Alliance for Research, Innovation, and Education, in short, AFRI. It's a non-profit 501c3 education organization meant for data science and public health in Ethiopia. And I will outline some of the activities, major activities that we are doing in public health and data science in Africa. So I'm not going to go to the mission and vision of AFRI. As you can see, there's a website. I will put also on in the chat. You can register part of the activity. So I'm not going to discuss on this, but most importantly, the goal of AFRI is to share knowledge, and everybody would like to achieve to have a full potential, exploit his potential or potential for the benefit of humanity and anywhere else, including Africa. So these are over 250 volunteer members, primarily from diaspora. As you can see, we have experts from all over different disciplines, but today I'm going to talk about the data science and public health area. So what are the major activities we are conducting? The first thing we put a year ago in 2021 is a very comprehensive article. Probably you can find it online, which we call it a roadmap for building data science capacity for health discovery and innovation in Africa. This has been cited by many until now, but we've outlined how training and capacity building look like to fully utilize the resources, the diversity that exists in Africa. So I encourage everyone to look at this article. So the other activity related to data science, we offer regularly a 3-day workshop, a virtual workshop. So that workshop actually pull people all over Africa, but primarily our host universities in Ethiopia, but we have multiple experts in data science, statistician, bioinformatician to offer this three days of workshop. And this year's workshop is scheduled for October. So I encourage you to look at our AFRI website. And this workshop, this is a hands-on data science workshop. We provide a lot of topics actually, but most importantly is a hands-on workshop using machine learning and our approach. And as you can see, we have diverse topics of the area from different universities. Most importantly, I think we try to link the 3 pillars of health data science. The domain knowledge, which is very important, clinicians, epidemiologists, genomists, or whatever domain knowledge you have, and the computer science, the computational skill, and the statistical, the mathematical. So there are a number of topics covered in this workshop. So in one of our meetings, as you can see the list of universities that attend, we actually pull over 1,800 students or attendees all over the different universities, including Ethiopia, other African countries, and anywhere else in Europe and in North America. So we couldn't even manage to handle in Zoom. We have to use other webinar systems. So there is a lot of interest in this kind of workshop. And we also ask participants what went wrong, what went good. So we have also, we have a survey values that shows what we're doing good and what went to improve in the future. So that was good for us in moving forward. The other workshop we give is related to data sciences, how to write the public health data science grants. We provide this workshop very regularly, very frequently, and we pull people across the different world. So if I tell you some of these people, some are from Canada, from Australia, from Germany, and from South Africa. So we have NIH and NSF people. Dr. Zaga is from NSF. So we have people from different area, background, different expertise that share their expertise in grant writing. And again, we provide a survey about the grant writing workshop, what went good, what went need to be improved, and we have really good feedback from the participants in this aspect. And also we ask them what they want to look in the future. So what kind of workshops they want in the future, not just the same data science or grant writing. Some of them mentioned statistical genomics, systematic or scope review, infectious disease, statistical design, grant writing, manuscript writing, even molecular breeding. So there are people from different areas. So data science doesn't mean only health sciences. People that are also interested in molecular breeding in a different area. So we're planning our future workshop according to the demands of the participants. And another aspect which I feel very strongly and very important is what is the follow-up mentoring? We can give a training or a workshop in 1, 2, or 3 days, but what about the follow-up? So we give a 1-year long-term follow-up mentorship for those interested to develop their grants or their manuscript to fruition. So we have, as I mentioned, we have 250 members. So we distribute according to their expertise to those mentors. So we want them to engage at least in a 1-year minimum, but that may go beyond that. And another aspect we provide is a monthly public health and data science seminar series at the Bahir Dar University. So this is really a very important seminar. We provide a virtual seminar every month, the first Friday of every month. And as you can see, people are from different areas, from University of Utah, from Oregon State or Oregon Health Science, you name it. We have people from different areas, different institutions. We provide titles ahead of time. We post this in our website, in Twitter or LinkedIn. So anyone interested, this monthly seminars, you are welcome to join us. Again, this is reaching out not just in Ethiopia but beyond that. And one of the workshop seminar we gave is African Genome Research. A well-known, a very talented expert, Fasil from NIH, outlined about the potentials of genomic research in Africa, how to improve public health. And there are a lot of participants, as you can see, in our meetings. And also another aspect I want to mention is that we also now developed a public health genomics program at the Bahir Dar University at MPH level. So we're really actively engaging data science and public health genomics in Africa. So as I mentioned, our goal is to create expert-oriented database, faculty mentoring. Mentorship is our really important goal. We want to transfer knowledge from Western countries to our Africans. And also our goal in this AFRI is to create a platform so that people can partnership with an African institution and beyond that. So in public health, and it could be other areas as well. So anyone interested, I know I'm a little bit rushed because of time, but this is a website where you can, afri.org, you can register and you can participate actively in this area. As you can see, we register in this area. You can register based on your expertise. You can put data science or public health in other areas. So we want to have an expert-based detailed database. And these are the leader of the AFRI team. They have about 5 team leading at the moment, but we have over 250 members. Again, thank you very much. In Ethiopian saying, Amasagnalo. And if you have any question, any thought, you're welcome to give me feedback. Thank you again.
Thanks very much, Tesh, for that insightful presentation. So we will take our last presenter, who is Uduna. I hope I got your name right, from McGill University.
Yeah, that's right. Can you see my screen?
Yes, thanks. Go ahead.
Okay, fantastic. Let's just activate this. Okay, so this is really great to be here. I'm Dr. Udana Anazodo. I am a medical imaging physicist at the Montreal Neurological Institute in McGill, and I'm also the founder of the Consortium for Advancement of MRI Education Research in Africa, which is what I kind of wanted to talk to you guys about today. So I'm just going to talk a little bit about one aspect of what we do at Camera, which I think it's of interest to the group, which is looking at data science ecosystem, especially within medical imaging, and how we can start to plug in some of the gaps, especially in terms of, trying to do this in a resource limited setting. We sort of did a editorial about a year ago, just highlighting the fact that artificial intelligence can solve global and population health challenges if we can improve infrastructure, data quality, personnel, and policy challenges. And I think some of you may be aware of these challenges, but medical imaging, especially when we talk about imaging of centralized imaging and advanced imaging techniques like magnetic resonance imaging or MRI, there's a lot of unique challenges that we may have to bear in mind. I'm just going to highlight one of them. One of them is data quality, and also being able to know how well to anonymize and annotate data, especially when you're dealing with brain MRI data sets that may have the patient's face in the images. There's also issues with the fact that in Africa, a lot of the imaging devices, especially MRIs, are still what we call low field, so they're lower technology and they tend to produce lower spatial resolution, and poor contrast images. There's issues with data storage and archiving. If you can store and archive the data, then you don't have a digital data set to share, and that obviously limits ability to do data science or even artificial intelligence. And obviously competition infrastructure being a problem. There's issues with skilled personnel. We all are facing brain drain issues, but when it comes to very advanced imaging techniques, especially MRI, it's very subspecialized, both on the clinical interpretation side, so the radiology side, as well as radiographer, and even the medical physics. And now get into informatics or even being able to do biomedical research. And there's issues obviously around policy data, shared data protection, and even being able to get stable funding to be able to fund very expensive MRI research. I would just want to highlight this to sort of demonstrate why this is very important to include imaging data sets from Africa. Like I said, a lot of imaging infrastructure in Africa is still what we call low field, so low resolution. This is an example from a patient in Nigeria compared to a 3 Tesla scanner, which is a typical research scanner that you find here in the West. This is work done by Don Zhang when he was in my lab, just demonstrating the type of image contrast and image quality issues. We decided to take some of these data sets from Africa and try to use, well, I say state-of-the-art established segmentation methods to segment lesions. This is brain tumor and ischemic stroke. And we're able to demonstrate that when you apply some of these state-of-the-art methods that have been validated on the typical, like say, standard data sets you tend to find in the West, so they tend to fail quite miserably because they're not exposed and used to the type of image quality noise, large resolution, and also the few data sets that we tend to have in Africa. So the question is, how can we build this data science ecosystem when we have very little trained experts in place in Africa, especially for medical imaging, poor and suboptimized infrastructure, and actually issues with funding. In Camera, what we've done is we essentially created a network of MRI users across the globe, anybody that does MRI, that loves MRI, and wants to help us train experts in place, build a collaborative network, and help us optimize infrastructure. We welcome them because our goal is to create this unbroken chain of resources that will take the infrastructure that we have and optimize them so that we will be able to use them and do imaging research. We've come up with a framework which was informed with a needs assessment study. We did a 2-year needs assessment study. It surveyed about 175 clinics across Africa. We're able to put together a framework that includes advocacy, because a lot of the imaging devices that are from the continent are not directly bought from the imaging device or OEMs, or original equipment manufacturers, meaning that the clinics get them, they're not trained, they don't get the full capacity to use them. Some of them don't have access to the MRI sequences. These are the techniques that we need to use to generate the images. So we're working together with vendors to figure out how to close this gap, how to help us train a critical mass of experts in place. Together, by having that critical mass of experts in place, we surround them by a network, which will help them retain and sustain the knowledge they have to then lead into innovation. This is also summarized in our framework paper, as well as a few other publications that we have, again, targeting vendors and trying to pull them into this discussion on how we can train experts in place, optimize infrastructure, and create a collaborative network. I'm going to use this project we're doing right now in Camera called AFNA, the African Neuroimaging Archive, to demonstrate our framework and how we're implementing this framework in terms of being able to provide optimized infrastructure. We've got a grant from the Lacuna Fund. The grant initially was for us to actually create open MRI data sets that could be made publicly available for anybody in the world to use it to create data science or AI, artificial intelligence tools. We decided to use that funding to do a little bit more. As Africans, we tend to do more with little. So we used that money and coupled it up from other sources, and we're able to actually set up a medical artificial intelligence lab in Lagos, Nigeria. This is the first lab that is set up in a private clinical practice in Africa, and I think actually in the world, because this, when it comes to medical imaging, or when it comes to radiology, or even healthcare in general in Africa, most of the healthcare services are in private practice. And so we have to figure out how to engage private practices in how to do research and how to use their infrastructure, optimize it, and use it essentially to help them provide improved care. So we're able to get money to set up a lab in Africa. At this lab, we're doing a lot. One thing we're doing is trying to create open source picture archiving systems that can enable us to archive and store data and compress them well so that we can uncompress them and then use it later on for data science. We just wrapped up a MICI, this is the Medical Image Computing Computer Assisted Intervention Society Brain Tumor Segmentation Challenge. Challenge has been running for 10 years. This is the first time we're able to provide brain MRI data sets of glioma patients from Africa. Made it open. We had 186 submissions from across the world, and we also were able to train our own colleagues from Africa to participate in this challenge. We trained about 70 clinicians and imaging scientists or computer scientists and medical physicists to create 10 methods for brain tumor segmentation that were submitted to this challenge. At first, and to be honest, where we have that many Africans participating in an imaging challenge. Through this funding as well, we're able to retain a medical physicist and an IT specialist, scientist. Like I mentioned, we trained 70 MRI, trained 70 clinicians as part of this larger project. So we're able to use the data sets that we aggregated, and we're able to then essentially use them and create their own AI or deep learning methods. We're working on SOPs for ethics, for data governance and data sharing. And, one thing we have learned from this, being able to actually aggregate retrospective data is we're able to learn a lot about the nature of the imaging challenges that we have in terms of how images are acquired, how well people are trained, especially the radiographers, and how to acquire these images. So that's actually led us to create this brain tumor imaging guideline. This is a guideline for acquiring brain tumor images in low risk setting in Africa, where, for example, they use half contrast dose to acquire images, which is something unheard of. We don't do that here, but we have to figure out how to help them use their infrastructure very well, and that's one thing we're trying to do. So just to wrap up, one thing I want to point out is that when it comes to at least building an ecosystem for data science, we have this program. You can go to our website and learn a lot about it. We're going to run it again next year. So this is a program where we've designed this teach, try, use approach. We teach them a concept. The use case in this particular case is brain tumor segmentation. So we taught them everything from Python programming for image segmentation to image analysis for brain MRIs. We got them to try past open source brain tumors data sets, and some of those top performing models I mentioned to you that failed, we got them to figure out how it worked and why it failed, and then we got them to actually use what they've learned by participating in the challenge. We're doing this again in our SWIM program. This is a Scan With Me program where we're actually going backwards and training our radiographers to help us provide good data sets, again, using this teach, try, use approach. In this case, we're using cardiac MRI as a use case. We could flip it for brain or prostate or whatever, but the idea is to figure out a way to systematically train practicing radiographers to actually gain competency to use their existing infrastructure, figure out how to optimize their protocol and help us acquire high-value data sets. So this is actually running on right now, and we have a lot of support from the vendors, from Siemens, for Canon, from GE, from Philips.
Wrapping up now.
And lastly, we will be in November trying to figure out how to train our biomedical engineers to help us maintain the infrastructure, imaging infrastructure that we need so that we can be able to acquire good imaging data sets. So we're going to try to just teach people how to build an MRI scanner. If you know how to build it, then you know how to maintain it. So I'm going to end here, and I'll be happy to take any questions.
Thank you very much, Una, and a big thank you to all the presenters. So from here, I would allow my colleague Asha to moderate the Q&A session.
Thank you all again for presenting. If you guys have any questions, feel free to raise your hand, or you can also ask your questions in the chat.
I think we have Sola and Sumit.
Yes.
Sola, probably.
Yeah, thank you for the presentation. Yeah, you actually working on medical images and segmentation. So I want to ask the presenter, in your archive, is the image that you get from MRI, is it in 2D or is it a volumetric data? As in, does it have those images you have on your archive, is it volumetric or is it 2D data? If they are volumetric, so how do you segment and archive the volumetric data?
Assuming that question is for me.
Yeah, the presenter.
Okay, yeah. So the images are three-dimensional images.
Three-dimensional?
And yeah, so the three-dimensional DICOM images. So they're images, they're essentially the way they are when you acquire them from the system. We trained the radiologists on how to actually segment a three-dimensional images. We do this very simply and very easily here in the West. They've never done that there. So we provided them with tools on how to do that. We actually had to pay them. So we got a grant to actually help us pay them for their time to learn how to painstakingly annotate 150 images. So we have a protocol on how to do that, and it's not rocket science. It's something that we've already done very well in the West. We just help them learn how to do it well in Africa.
But the concern now is the images we are having now are coming in they are coming in 3D.
Yes.
Yeah, you understand? They are coming in 3D.
Yeah.
So, and in 3D, you have the Z dimension of it, the height, the depth dimension of it. So if you are segmenting, how do you now? Okay, so what?
So I think I know where you're getting at. So essentially, to segment a three-dimensional image, there's so many ways to do it. We are lucky enough that people have been doing this brain tumor segmentation challenge for 10 years. So 3 years ago, they came up with a deep learning method that actually allows you to start to pre-segment your images. So essentially, it's able to segment out the brain tumor, and then an expert like a radiologist will go in and refine the edges of the tumor. There's so many ways you can do it. You can do region growing method in a way to segment it. You can do, there's a lot of ways of doing that. So yes, we did it first by pre-segmenting it using DeepMedic. And then the radiologists were trained on how to refine to make sure that we're not missing out any edges. We were segmenting whole tumor, the core, which is the dead core, and the penumbra, which is potentially a viable, healthy part of the brain tumor. And so we're creating 3 different labels.
Yeah,
right, thanks very much, Una.
I would really love to see that, because I'm currently working on volumetric data segmentation for medical images.
Okay, you can send me an email, I'll send it to you. It's not rocket science. There's so many ways to do it. It's trivial. So I could send you an email on how to do that.
What I'm saying is this: I'm developing techniques.
Can you hold it, Sola?
Sorry?
I'm developing techniques, new techniques to handle that. That's what I'm getting at. So I'm actually interested. I'll get across to you.
So email me and I'll help you.
I would encourage all the presenters to drop their emails in the chat box so people can reach them. Smith, can you take your question?
Okay, so my question is for Dr. Dana. Thank you for your presentation, and it's really lovely work to see you doing. I noticed one of your graduates from Mombara University. I'm wondering, do you work with a mod research program or not? I'll put the URL in, and maybe Francis can give you my email, and we can continue this conversation by email. Thanks.
Sorry, I caught half of it. I heard Mombara University, and I didn't hear anything else.
I'm wondering, are you collaborating with the current project, DSI Africa project at Mombara University on biomedical imaging?
I am collaborating with Mombara University, but not on that particular project. I'm collaborating with Johnson Wungolosh on trying to build this head-only MRI system and a bunch of other stuff. But I'm happy to collaborate with you.
Okay, I'll put a URL in there.